Hello. Today, we'll talk about solving more exponential equations. So I created a previous video just called Solving Exponential Equations. So this is going to take some of those same ideas but kind of go beyond that. Let's take a look. So our goal is then be able to solve exponential equations and also, realize this is actually a typo. I should say be able to use, actually fix that one here, be able to use logarithms to solve exponential equations. There we go. Okay, so in my previous video, I did a few basic examples of solving exponential equations. A reminder, an exponential equation is called that because your unknown variable, what you're trying to find, is in the exponent, like this example we see right here. Okay, the x and the exponent, so you need to find some way to get essentially to undo the exponent or get the variable out of the exponent. So the first case I looked at in my previous video was a more simple case like this, where both bases are the same. So if you have one exponential expression equal to another, and both bases are the same, then use this property that says this, that if you have two exponential expressions like this, where the bases are the same, if these two things are equal and the bases are the same, that means the exponents must also be equal. Let's reuse that. Now, I want to come over here and take a look at a couple examples where it's not clear that they do have the same base at first. So let's come over here, and our direction will just be to solve. Let's look at our first one. Let's say we have this equation, 4x is equal to 2 times x minus 1. Now, obviously, right now the bases are not the same, so we can't use this property as it is. But what to remember, though, of course, is that 4 is 2 to some power. 4 is 2 squared. Okay, so I can rewrite this as 2 squared, like 2 to the x is equal to 2x to the x minus 1. Okay, now remember a rule of exponents. If you have exponents multiplied like this, you have one power raised to another power, you multiply the exponents together. So this becomes, finally, 2 to the 2x, 2 times x is equal to 2 times x minus 1. Then we just equate the exponents because the bases are equal. And so, of course, that gives us then 2x is equal to x minus 1. So subtract x on both sides. That gives us an x equals negative 1. And of course, you can always check that, plug that back in, and make sure that's true. Okay. All right, let's take a look at one more similar to that in concept to that. So number 2, let's say we have 8 to the x minus 3 is equal to the square root of 2 to the 2x. Okay. Now, this is another one where we can do a similar thing. It's not clear looking at it right away. Obviously, there's different bases at the moment, but we can actually write both as powers of 2. So we're going to write both bases as powers of 2. Okay, so 8, is 2 cubed. So this is 2 cubed to the x minus 3. Now, hopefully you remember that exponents or radicals, roots and so forth, squared can be written as a power. A squared is the same thing as the 1/2 power. This is the same thing as 2 to the 1/2 and then times 2x. Once again, using that same rule we mentioned before. So when you have an exponential expression raised to another exponent, you multiply the exponents together. And so this is going to be then 2 to the 3 times x minus 3. And this then, of course, is equal to 2 to the 1/2 times 2x. And then that's going to be 2. If we distribute the 3x minus 9 is equal to 2 to the x. Okay. And now, once again, since the bases are equal now, they're the same, this implies that if this expression to be equal, the bases are equal, then must mean the exponents are also equal. So we have 3x minus 9 is equal to x. And then here, I think we'll just add 9 to both sides. So if 3x is equal to x plus 9, and now subtract x on both sides, that's going to be 2x is equal to 9. So finally divide both sides by 2, x is equal to 9/2. So that's our answer. So if we can do that, that will certainly be the best way to do it. If our bases, both our bases, are something that can be written to the same power. Now, what happens if that's not the case? So let's look at an example here. This will be on number 3, and we'll explain it over on the left. So let's say we have 5 is equal to 2 to the x plus 3. Okay, so let's go back to the left. So this is what I call case number 2. In case number 2 is basically you can't do that. So it's not impossible. There's no easy way to write better 5. There's no easy way. Oops. There's no easy way to make there's no easy way to make 5 as a power of 2. It's not impossible. But also you have to use decimals or something like that. So there's another way of doing this. So let's take a look over to the left. You have something like this, or like both examples, we'll also do this one in a moment. So you can't easily do that. You can't easily write both bases as something. So we use a property of logarithms. We're going to use logarithms to help us solve this. So the property says if you have two things also have to be positive numbers, m and n, that if m equals n, then if you take the log of the same base of both sides, that's also equal. Okay. Now remember, exponential expressions are always positive. So these are 5 is positive, 2 to the x plus 3 is positive. So what that means is that I'm going to take, and also it doesn't matter which log you take, but take some log of both, and then that way we can solve that. Now, the best one to use is either log base e, natural log, or log base 10. You can use others, but those are the ones most commonly found on a calculator. Most time, although we'll get an exact expression in terms of logs, it's not very useful. We need to be able to approximate it to find some value in it. Yeah, so it says to solve this type of equation, take a logarithm of both sides to get the variable out of the exponential expression. That's our goal. Remember, with being an exponential equation. It's best to use natural logarithm or base 10 logarithm since your calculator has those buttons. All right. So here, and actually we're going to do this one with both to show you get the same thing. So and here's, I'm going to say take, and let's start with log base 10. So take, remember, log base 10 is log of both sides. So what that's going to give us then is log, or log of 5, is equal to the log of x plus 3. Now, a property, remember, property of, I'm sorry, hang on. We're going to write the right log of 2 to the x plus 3. There we go. Now remember, log 5 is just a number, and log base 5 is also just a number. Okay. Now, we use a property of logarithms. The reason we do this is I can actually take this exponent and bring it out front. That's the property of logarithms. And so then this is going to be log base 5 is equal to x plus 3. I need parentheses here, so I'm multiplying the whole thing times log of 2. Remember, log of 2 is just some number, just a number, just a constant. Okay. Now, remember, the goal is to get x by itself. So divide both sides by the log of 2. And then we have this, the log of 5 over log of 2 is equal to x plus 3. And then finally, I just subtract 3 from both sides. And so, I'm going to turn this around, then x is going to be equal to the log of 5 over the log of 2 minus 3. Okay, and that's my exact answer. Now, that's not all that useful. So what we'll do here is a moment, we'll go back and we'll do that. We'll approximate this. Let's hang on that for a minute. So this is my exact answer. or an exact answer, one way to write it. Okay. Now, let's also do the same thing. I'll call this, I guess, number 4. So 5 is equal to 2 to the x plus 3. But this time, let's take natural log of both sides. So I'm going to show you that you can take any log. This will work for any base log, but these are the best ones to use. So take natural log, or ln, of both sides. So if we do that, we have natural log of 5 is equal to the natural log of 2 to the x plus 3. Everything here is basically the same. So once again, a property of logarithms, I can bring my exponent out front. And so we have the natural log of 5 is equal to x plus 3 times the natural log of 2. Or natural log of 2 is just a constant, so is the natural log of 5. As we did before, get the x by itself. So divide both sides by the natural log of 2. And so we have the natural log of 5 over the natural log of 2 is equal to x plus 3. Okay, and then once again, subtract 3 from both sides. I have x is equal to the natural log of 5 over the natural log of 2 minus 3. Now, let's approximate this. I'm actually going to use Desmos. You may be familiar with Desmos from using it from graphing, but actually we can also use Desmos to approximate things or calculate things. It's also really useful for that. So let's go to just click on graphing calculator. Now, remember what I have is log of, let's double check, go back and take a look. So log of, let's do this one first. Log of 5, natural log of 5 over the natural log of 2 minus 3. So let's do that. Now, to find those buttons, there's a keypad enter, click on that. And then if you look at functions, go to functions. And I believe, well, it's not, All right, here we go. Yeah. So ln and log. There we go in the calculus function. So do natural log of 5, then divided by, so do the same thing, back to functions. Natural log of 2, then minus 3. And see, that's approximately, and let's approximate it 3 places for now. So approximately negative 0.678. This is approximately negative 0.678. Okay. Now, I'm going to show that actually if you use log instead of natural log, you get the same thing. So let's go down here. Let's go back to the same functions, the calculus functions. Let's do the same thing with log, L-O-G. So log of 5 divided by log of 2 minus 3. Okay, we see exactly the same thing. Now, to be clear, a couple things to mention. The natural log of 5 and the log of 5 are not the same. Okay, those are different. It's the same way the natural log of 2 and the log of 2 are different. You can check that. But these fractions, natural log of 5 over the natural log of 2, is the same as the log of 5 over the log of 2. So these are equivalent. So actually, what this shows, you can use any log base you want. You can even use log of 3 or log of 10 or log of 7, something like that. But it's best to use natural log or log base 10 because those are most likely to be like almost all scientific calculators or graphing calculators have those. That's the best choice to use. Okay, so let's go back up here and then just mention that's the same thing. So this is also approximately negative 0.678. Okay, now let's do this next one then. Now, so I guess this will be number 5. So this time we have 3 to the x plus 1 is equal to 7 to the 1 minus x. Okay, same thing. There's no easy way. It's not impossible. You have to use decimals to write, 3 is 7 to something or 7 is 3 to something. So we're going to use logs. And this time I'm not going to do it both ways. I'll just pick one. And this time I'll just use natural log, but it doesn't matter. So I'm going to take ln of both sides. And so that's going to be the natural log of 3 to the x plus 1. This looks like a plus. And this is equal to the natural log of 7 to the 1 minus x. Now, on both sides, we use the same property that my exponent, because it's a logarithmic expression, my exponent is going to come out front. And so here, then what we have is x plus 1 times the natural log of 3. You know, the natural log of 3 is just a constant. And 1 minus x times the natural log of 7. The natural log of 7 is also just a constant. Okay. Now, this one requires a little bit more work. So remember, our goal is to get x by itself, but notice we have an x on both sides. So actually the best thing to do here is actually to distribute. It's not the only way. It's probably the best way. So what I'm going to do is just distribute the natural log of 3 to both terms and do the same thing over here with the natural log of 7 on this side. Okay, so we have x times the natural log of 3 plus 1 times the natural log of 3, or just the natural log of 3, is equal to 1 times the natural log of 7, or the natural log of 7, then minus x times the natural log of 7. Okay, now, maybe wondering why we did that. Well, this way we can actually get our terms involving x on one side and our terms just involving just natural logs or just constants on the other side, the same way we do in solving any kind of equation. So, it doesn't matter, but let's actually add this term to both sides. So if I do that, I'm going to have x times the natural log of 3 plus x times the natural log of 7 plus the natural log of 3 is equal to the natural log of 7. Okay, so I just added this term to both sides to get it over here. Now let's subtract this term from both sides. And so we have x times the natural log of 3 plus x times the natural log of 7 is equal to the natural log of 7 minus the natural log of 3. Okay. Now we're almost there. So remember, our goal is still to get x by itself. So what I want to do on this side is I actually want to factor out x. So I want to factor an x out of the terms on this side. So just take an x. Remember, factoring is like distributing in reverse. And so if I take an x out of both, what I have left then is the natural log of 3 plus the natural log of 7. You can check that if you want. So remember, you always check, multiply it back through. If you distribute the x, you get this. Now, the right side is still the same for now. Okay. Now, actually, we're just have one more step. Now, as I said, mentioned that both these are constants. The natural log of 7, the natural log of 3 are just constants. And so if you add them together, that's also just a constant. So what I'm going to do then is just simply divide both sides by this. The natural log of 3 plus the natural log of 7. And also one more thing to make clear, remember that you can't cancel these out. Okay? If they're all multiplied together, if these are multiplied together and these are multiplied together, you cancel them out. But since they're part of addition to subtraction, you can't cancel these out or these out. Okay? Now I can cancel this because it's the same term on both top and bottom. And now we just have x. We now have x by itself is equal to natural log of 7 minus the natural log of 3 over natural log of 7 plus the natural log of 3. Okay? Now, that is the exact answer, but as you know, so that's not all that meaningful. Now, one more thing I'll mention. I'll say also, if you had used log base 10, then x would also be equal to, I'll say also if, I'll just say used another log, then you just essentially replace, what would happen, this would be good practice to do on your own, is just use log, L-O-G, and you'll see you get a similar expression. Essentially you have, instead of ln, we'll have log everywhere. So you'd have log of 7 minus log of 3 over log of 7 plus log of 3, okay? Or if you use, say, base 2, you'd have log base 2 of 7 minus log base 2 of 3, and then just log base 2 of 7 plus log base 2 of 3, okay? Now, let's approximate this. So let's go back to Desmos. Okay, let's go down here. And so one's going to use those same functions. So ln 7. Now I believe I can also just simply just type that in though. So ln 3. Okay, we can also get it that way. Now also, if we want to divide this whole thing, we need to, if you just try to divide it here, then it'll only just divide, if you just use the division there, it will only just divide the bottom one. So what we want to do is put these in parentheses. So it will divide everything. We want to put a denominator under everything. And so now just ln 7 plus ln 3. Okay. And so our result, once again, I'll use 3 decimal places. That's convenient. So 0.278. That's approximately 0.278. And once again, if you check and replace the ln with log, you'll get the same thing. Now, once again, as I said, the natural log of 7 is not the same thing as the log base 10 of 7 or the same thing as log base 2 of 7, but these fractions are equivalent, or even the numerators are not necessarily the same, but these fractions are equivalent. Okay, so let's review. So what we learned is that if you have an exponential equation where the bases are the same, or the bases can easily be written as the same, in this case, like these, then we can just use this first property and set the exponents equal to each other. Or if you have a case like this, we'll call case number 2, where you can't do that easily, then you can use logarithms, take the log of both sides, any log of both sides, and use that to solve the exponential equation, because what that will do is allow you to get the exponent out of the, or get the variable out of the exponent, which is our goal, then solve for x. So that's how you can solve exponential equations. Thank you. Have a good day.